Okay, we are in the last topic of section 15.1 about the Rodrigues formula. We have already talked about the Rodrigues formula for a general case for general orthogonal polynomials in section 12.1. So in section 12.1, we have the general formula. So this is for equation of this form. Now this is the form of the Rodrigues formula with W given by equation 12.7. Now we are applying for the special case for the Legendre polynomial. So the Legendre equations is this one. So compare with the general case, P is 1 minus x squared and Q is minus 2x. So, and we have talked about that this is the case for a self-adjoint equation. So pretty sure W is 1 for a self-adjoint case. But if we apply to the general formula, so using this P and Q, and using this formula, we can say, check that this is the case. So P is 1 minus x squared, and this is a exponential function, and the integration of Q over P, so integrating minus 2x dx over 1 minus x squared. So, and then we can simplify that to this is like 1 minus x squared exponential function, and change that to this integration can change to dx squared over 1 minus x squared, because dx squared is minus 2x dx. And once you integrate that, that becomes a log of, I should say, exponential of log of 1 minus x squared, with the choice of your lower bound, of course. And then exponential of log is just give you that function, so 1 minus x squared divided by 1 minus x squared is 1. Okay, so for this case, you can apply for the Rodrigues formula. W is 1, P is 1 minus x squared, so Yn. For the Legendre equation is given by just taking nth order derivative of 1 minus x squared to the power n. Okay, so this is equation 15.29. Okay, so this is a solution for the Legendre equation. And of course, this is different from the Legendre polynomial by a factor, because by convention, Legendre polynomial defined by the boundary value P at x equals to 1 for all n. So, and to get to that convention, we go back to the generating function, and remember when we talk about the generating function, we multiply by a value which is the same value as we multiply by here. So the value is minus 1 to the n power to 2n divided by 2 to the power n and n factorial. So we multiply, so Pn x is defined as this factor, so minus 1 to the n power divided by 2n to the power n factorial multiplied by this yn. Okay, and this minus 1 to the n power you can use to flip this sign of this factor. So that becomes 1 minus 1 over 2 to the power n factorial, and for the derivatives of x squared minus 1 to the n power. Okay, so this is the Rodrigues formula for the Legendre polynomial defined conventionally. So this is equation 15.30. All right, and one little check that this give back the conventional value is the leading order of the polynomial, which is x to the power n. For Pn, the leading order x to the power n, and we got that by this term, so the highest order x to the 2n power, and you take the n derivative, you reduce it back to x to the power n, and the coefficient, so coefficient of xn in this is given by just taking n derivative of x to the 2n. So with this same coefficient in front, and then take the n derivative of x to the 2n, so you have 2n factorial divided by n factorial. Okay, and then I mean, you can leave it like that, but you can also use the double factorial notation, because you 2n factorial divided by n factorial, so you get all this 2 to the power n. Each one you divide, you get a factor of 2. You get 2 n of them, you get 2 to the power n, so you cancel with this 2 to the power n. So that becomes 2n. Minus 1 double factorial divided by the just 1n factorial. Okay, and this is what we got from equation 15.13. Okay, this is by the generating function. We got the same coefficient. Okay, so that shows that this is the right definition of the polynomial, Legendre polynomial using the conventional definition.